Hello ladies and gentlemen, my name is Dr. Simon Schmidt and I'm head of the Department of Hygrothermics at the Fraunhofer Institute for Building Physics, IBP. In this lecture, you will be introduced to the basics of heat and moisture transfer. You will see the impact of the construction used and will see some possibilities to optimize this construction in terms of heat and moisture protection. In former lectures, you have learned about the balancing equation, also from the energy efficiency perspective, but also in its singled out components. This time, we will have a look at the last missing part of this balance. The last part of the balance deals with the internal loads. These are mainly people and electrical applications, but also showering and cooking generates internal heat sources. These internal heat sources can be calculated in two ways. The first way is to use an average internal heat source, which can be calculated by multiplying the living area by 40 watt per square meter. In the case of the lighthouse project in AGARTALA, a living area of 26.78 square meters results in a heat source of 1072.2 watt hours per day. But this is without the energy from persons in the room. For more accurate calculations, however, a second way can be used: the floor plan and existing electrical applications as well as the people present to be taken into account here. In the example shown, one person lives in the apartment and is present for an average of 8 hours. In the apartment is one TV with 100 watt, which is switched on about 1 hour per day. Furthermore, a laptop with an average of 60 watts is used 1 hour per day also. The lighting of the apartment is done by 5 lamps with 10 watt each, which are active for about 5 hours. The last device in the apartment is a refrigerator with 150 watts. This consumes half the day of active power. If we multiply these numbers and sources with the average activity time and their current power consumption, we get the daily consumption of each item. This adds up to the total consumption in the apartment of 3000 watt hours. How much the interior is heated by these sources depends mainly on the storage capacity of the room. The storage capacity mainly depends on the material used for the components. But let's have a look at the storage capacity itself. The storage capacity of the lighthouse project in AGARTALA is highly variable. There are 3 different types of concrete to choose from, as well as insulation material. In the table, the specific heat capacities for each material is listed. Basically, the higher the value, the more energy the material can store at the same volume. To get a better idea of heat storage capacity, it can be compared with batteries. The higher the storage capacity, the more energy can be stored in the form of heat into the material. As long as the batteries are not fully loaded, heat can be stored in the building by internal sources and does not increase the room temperature. Let's consider this phenomena in the case of the lighthouse project. When examining this connection, it quickly becomes apparent that the use of concrete with high storage capacity has advantages compared to insulation material with low capacities. Due to the high storage capacity of concrete, energy which is introduced by internal or solar loads can be buffered for a long period of time, preventing rising temperatures. In the case of insulation, if the same amount of energy is introduced into the room, an increase of the room temperature is much faster observed. As we have had a look at the internal loads and the storage capacity of the building, now let us have a look at the interaction between these two aspects. To display the influence, I have performed some simulations using AGARTALA flat as the basis. On the left, you see the variance in which the internal storage capacities was changed. Low means we use insulation on the internal walls and the external ones. High stands for insulations on the outer walls and concrete on the inner ones. The same goes with the internal loads. Low means just one person living in the flat. High, that a family of 4 is living in the same flat. If we now look at the hours in which the room temperature is in one of the 4 thermal comfort zones, which you can learn something about in another submodule, we see that it varies depending on how we vary the combination of concrete and insulation in combination with the internal loads. If we insulate the walls on the inside, we decrease the storage capacity of the concrete through the insulation. The result is that the building becomes too warm during the day and too cold at the night because too little energy has been stored in the building fabric. If we insulate the walls from the outside, the higher storage dimensions can be used. The findings of this simulation is that if we add internal loads, which are mainly people and electric devices, we need high heat storage capacities. This will buffer the heat during the day and cools down at night. The main thing here is that we have to unload the storage capacity during the cooler nights through, for example, night ventilation or other measures. By doing so, one can increase the thermal comfort directly by using basic building physics knowledge. And with this, I would like to say thank you for listening and goodbye.